Welcome back to the continuation of the lecture for the exception and interrupt. In this video, firstly, let's look at the processor call interrupts. There are a few types of the microcontroller interrupts. The first one, which is the hardware interrupt. In terms of the hardware interrupt, the behavior is asynchronous. It is because it is not related to what code the processor is currently executing. And hardware interrupt is where the interrupt signal which is sent to the processor from an external device. So that is why when an instruction is being executed within the processor, it is not related to the interrupt inside the processor, where this hardware interrupt is responded or interrupted by the external device. For examples, when interrupt is asserted, character is received on serial port, or it can be the applications of when the ADC converter finish the conversion. Let's think about a more simpler example. So when normally we press a keyboard button or when we move our mouse around, they will trigger the hardware interrupt because keyboard and mouse, they are external devices. So when we move or we press a key button, it's basically we create a hardware interrupts. In other words as well, if based on the year 2 Java programming you have learned, it's like an event. So your program code in Java keep on listening to an event. As I mentioned in the first part of the lecture, an event is also an interrupt, right? An interrupt is what we use in the term for the microprocessor. Okay. So when the hardware interrupts occur, this will cause the processor to read the key stroke or the position of the mouse currently, right? And the next one I'd like to talk about is the exception faults for the software interrupts. And for the software interrupt, the behavior is asynchronous because it is the result of where the specific instructions are executing. So it can be the examples of through the undefined instructions when you have overflow instructions that occur for a given instructions, right? So this can be due to I can talk about an example when you try to divide a number by 0. Of course, we know this will cause a divide by 0 exception error, in other words, right? So this will cause the computer itself to not to continue, abandon the calculation, and eventually it will display the error message. So software interrupt instructions work similar to the subroutine code. In other words, is in the synchronous manner. We can also enable or disable the mask of the most interrupts as needed, as could be maskable or it could be non-maskable. So remember about the bit mask operation. So it is to clear, change, or remove any unwanted bits as what we required, right? But some masks are non-maskable, like the watchdog timer is non-maskable. Next, I'd like to talk about interrupt service routine. This has been covered in the past lecture, during the live lecture many times. So interrupt service routine is a subroutine which processor is forced to execute to respond to a specific event. In other words, ISR is a signal, right, to the processor emitted by the hardware or software. So it can be from software or it can be from the hardware, right? Indicating that a handler that needs immediate action or an event that needs immediate actions. Okay. So when an interrupt occurs, the controller will complete the execution of the current instruction. Remember, I told you in the last lecture, it's the current instruction rather than the whole program, and it will start the execution of the ISR, or in other words, interrupt handler. The ISR will inform the processor or controller what to do when the interrupt occurs. For example, we have the exception numbers, and also like what you have learned for the EXC return. So whether you'll be returned back to thread mode or the handler mode, right? The interrupts can be either, as I mentioned, hardware or software interrupts. And finally, after the ISR completes, the microcontroller will go back to the previously executing code. So it means that it will run back to the thread mode. Up to now, you have learned the core concepts inside the interrupts, like how it operates, how it returns the mode, so that we can determine whether you'll be in thread mode or handler mode. Now, in this slide, I'm going to talk about how we are going to assign the interrupt based on different priorities. So, this is done through the NVIC, or the Nested Vector Interrupt Controller. So the Nested Vector Interrupt Controller is a method of prioritizing the interrupts. This is to improve the microcontroller's performance and, of course, to reduce the interrupt latency. Okay, so in this figure, for example, you can see there are 3 modules, and then they are connected with NVIC that forms the part of the ARM Cortex core. I would like to let you know that for this NVIC, it can be within the port module itself in the NVIC for the GPIO, general purpose input and output, for example, or it can be based on the external devices, right? So bear in mind, NVIC, when you look at this term, it is to deal with the priority. Next, I'd like to talk about how we can know the exception number for the NVIC. Remember that you have learned the exception number, so there are a range of exception number to deal with the interrupt. So you can look into that in slide number 17. Okay, so to deal with the internal interrupt, it starts from 1 up until 15. So that is the interrupt within the ARM processor core itself. Then from 16 up to N, we can have the interrupt that is going to respond externally, right? So remember, like 1 to 15, we have the reset, hard forward, and then reserve. And for these onwards, the external one, we can have IRQ 0, and then IRQ 1, 2, and so forth. So these are the external interrupts. Okay. So the Nested Vector Interrupt Controller manage and prioritize the external interrupts. So as I mentioned just now, interrupts are types of exception. There are 16 exceptions you have learned for the internal, and with an additional extension from 16 onward for the external interrupt that corresponds to the IRQ and then 0 and so forth, right? 0, 1, 2, and so forth. And this is what we have learned, because interrupt, we can have thread mode or handler mode. So in the thread mode, once the interrupt has been initiated, it will enter on the reset mode, because for the thread mode, it will run in the main code. The next one, the handler mode, is where it will enter on executing an exception. This is where we will have the ISR, interrupt service routine, to initiate the response of the interrupt. Of course, it is run based on the different privileges level. In terms of the step pointer to deal with this, it's the same what you have learned so far, MSP and PSP. Okay, right. So how does this NVIC works? You can see the keywords here nested that provides the key definitions, right? So the term nested here basically refers to the fact that inside the NVIC, there will be a number of interrupts. So the interrupt is not only one or two, it can be hundreds or thousands more that we can, it's difficult to say anyway. And each interrupt will be assigned with a priority, regardless of how many interrupts are there, right? And how we can know that the level of priority, we can set the priority value. Like for example, 0 is the highest priority, okay? Most critical interrupt, like the most important interrupt, can be made non-maskable. For example, the watchdog timer, which is non-maskable, meaning that it cannot be disabled, so it cannot be masked, right? So there are some kind of devices or some other component we would like to make it non-maskable, so we won't do any interruption on that device, as I mentioned just now, the watchdog timer. Right. So the next one is, we know that NVIC is to control the interruption based on priority. So how priority can be controlled? It is always ensuring that the highest priorities are being completed before the lower priority interrupts. As an example, if a lower priority is triggered, then the lower priority will run if there are no other priority higher than that. But if the lower priority interrupt is being registered and currently executing the instruction while a higher level interrupt is happening, so what will happen is, right, so I have lower priority and then I have higher priority, and the lower priority, now we have thread executed code. So when these higher priorities comes in, the CPU will not look into the lower priority task. It will finish only the current instruction and immediately jumps into the higher priority. So once this has been achieved, completed, it will go back to the lower priority doing the task. So you can see, basically, in this slide, it tells you another dimension of what you have learned so far, where now you have different priority, but the mechanisms of the flow is the same, right? So it's just that you have additional sub-level to deal with different priorities, but the mechanisms of handling the interrupt with the ISR, responding to the exception, so forth, they are the same. So in terms of the NVIC, there are a few exception states, which are inactive, pending, active, or even MP, right? In this slide, we are going to look into the NVIC registers and stack. It is very straightforward how we can enable and set or clear the interrupts, right? So the first mode is where we can have enable, right? So enable is to allow interrupt to be recognized by the microprocessor. So how this enable can be recognized? It is accessed through the two registers, okay? So it really based on how we set the bits inside the address for the interrupts. How to access these two registers? They are ISER and ICER. So we can enable the interrupt by setting the enable to the NVIC ISER, or if we want to disable or clear the enable, then we just clear it with ICER and we put the bit 1 into the corresponding address. So in the CMSIS interface, right? So these two are the similar way of allowing the interrupt to be recognized. But CMSIS provides a better interface, right? Allowing us to recognize putting the information in, and it will be recognized for the interruption. So it is just enable IRQ or disable IRQ. So it is very straightforward as it is. So not that these two are the same way for the NVIC to be recognized, right? Also, we can have the NVIC in the pending state, which is very interesting. We can initially assign an interrupt for a particular vector for the NVIC. So the interrupt has been requested, but we do not require it to run for the service. So priority is being set for the interruption, but it's still pending. So it's like it's standby for becoming alive to provide the service required. Another way how pending can happen is when the CPU disable the interrupt. So the previous running enabled interrupt, right, will be disabled. So that means it will jump back into the pending state. And this will become alive again. We don't know whether it will become alive or it will be disabled or being disposed from the system. It really depends on the nature flow of the program. But I just wish to inform you there are the possibility of how this can happen, right? In the CMSIS interface, it's very straightforward. You can just use stat pending IRQ correspond to which IRQ number for the interruption. Then the clear pending IRQ to determine which IRQ number for the clearing pending mechanism. For the co-exception mask register, it is similar with the global interrupt disable bit in the other microcontroller. PRIMASK or the priority mask register is the example of the exception mask register. The bit 0 of the PRIMASK is set as the PM flag. This is to set to 1 that prevents the activation of all exceptions except apart from non-maskable interrupt. So we cannot avoid that. And the next one is the hard fault, right? And those exceptions for the rest we cannot prevent. We prevent it with the configurable priority. Alternatively, we can clear to 0 to allow the activations of all exceptions. So we know bit 0 is the PM flag status. Then the bit 1 to 31 of the PRIMASK is reserved. So we do not need to care the rest of the operation for now. The PRIMASK is accessed using CPS, MSR, and MRS. So the CPS instruction is the change post state instructions. And then we have MSR, which is move to special register from general purpose register. And finally, the other way around, move from special general purpose register from special register, right? The most important goal target for the PRIMASK is to prevent the rest condition of the data with the code needing atomicity, right? So that's very important. In terms of how we can use the CMSIS core API interface to write the primas is the following. Okay, so the first one is we can use the enable IRQ that clears the PM flag, and then disable IRQ to set the PM flag, because this disable function here, when we set it to 1, it will prevent the activation of all exceptions, right? And when we enable it, we should clear the PM flag. So this is how it works. So set the PM flag to disable it, and then enable the interrupt by clearing the information in the bit 0. Then we can use get primas to return the value of primas. And finally, we can also set the primas to X as an example. Now the interesting bits comes in. How we can determine the prioritization. So the exceptions are prioritized to order the response simultaneous request. So what does it mean here is, if we have multiple concurrent interrupts with different level of priority, then it will be prioritized for the exception, where smaller number means the higher priority, right? So let's take an example. If I have the X priority is being set as 9 and Y the priority is being set as 5, right? Just an example. So Y has the higher priority than 9 or the X. So this is how it determines. Some exceptions for the priorities are fixed, especially for the reset, non-maskable interrupt, and hard fork. They are being fixed like -3, -2, and -1, where reset is the highest priority. Of course, if we are thinking about external devices or other peripherals, the priorities of other peripheral exceptions are adjustable, and the value is actually stored in the interrupt priority register from 0 to 7. So this is how it works, as starting from 0 to 7. To deal with the special cases of prioritization, let's look at some possible scenarios below. The first one, what happens when there is a simultaneous exception request? Of course, remember, the lowest exception type number will be service first. You can look or refer back to the slide 17 of the vector table. Or from the previous slide, I've already mentioned the internal interrupt for the reset, non-maskable interrupts, and the hard fork, where the reset comes with the highest priority, right? So remember, just change the color, reset has the highest priority, then followed by non-maskable interrupt, and then followed by the hard fork, right? Of course, there are few more than that, so you feel free to have a look at the vector table. In the next scenario, what happened, especially when the new exception requested while a handler is still executing? So that's a very interesting question, where we can look at the sub cases here. The first one, where we have the new priority higher than the current priority. So that means that it's a nested interruption, right? Because the interruption is still working on the current instruction, and then the next level of instruction comes in with the higher priority. So this is what it means. Therefore, the new exception handler will preempt the current exception handler. So it will finish the current instruction as soon as possible, then it will jump to the task with the higher priority. So the one with the lower priority will be stopped from the execution. Then the cycle loop of how the exception is being thrown, and with the exe return, everything else stays the same before it comes out from the inner loop and then goes back to the lower priority to continue the task. Another case is what happens if the new priority is lower than or equal to the current priority. So the new exception basically will held in the pending state. So instead it's being run, but the exception, the new priority is being waited in the line. So it's in pending, standby, right? And the current handler will continue to finish the execution, right? And what happened is the previous priority level will be restored. And finally, the new exception, which was in the pending state, will come in and will be handled if the priority level allows. So that means in the next round, this new exception comes with the highest priority, so it can execute the task, right? Let's look at the behavior of the interrupt through the timing analysis. The timing analysis is very useful as it gives a very big picture timing about how external events or the handler relate to the processor activities. As an example here we can see how long the switch was pressed and what the MCU did in the response, right? So you can see basically the switch was pressed for about 0.21 seconds, right? And then when there is a switch being pressed, an event occurs, or in other words, there's the interruption. So how to deal with the interruption? The ISR will run in response to the switch signal's falling edge because there's a changes in the output here of the switch. However, when you look into the main output window, you cannot see very obvious what's the changes, right? It seems to be running continuously because the signals may be toggling between 1 to 0, but the output is like, you can see it's fully white color, which is full, right? So it's running continuously. Therefore, it's not very obvious to look into the behavior. So you will investigate this further in the lab exercise. The other possible scenario to be interested with is the latency, right? The latency, in other words, is the time delay. So why do we care about the latencies? Of course, for the interruption, the smaller the latency, it will be better, because when the latency is small, then that means the mechanism or the time to deal with the interrupt is shorter. That is why we care about it very much. If you have high amount of latency, that means you have high amount of overhead that will cause a lot of time wastages, and this will increase the overhead because the interrupt rate rises. So it doesn't mean that you have interrupt that is a good news. As long as we have to properly optimize the amount of interruption, then we can minimize the overhead and also minimize the latency, right? So if we have high latency, of course, it will delay our response to external events. And then there are many other subsequent tasks that are being queued to be triggered will be delayed as well. So it is not acceptable for the application, right? So you can think about sampling an analog waveform, but if you have too much latency, then it will create a problem with not accurately capture the waveform of the analog. Okay, so basically how long we need to take for the latency for the interrupt response, right? Of course, we need to finish executing the current instruction or abandon it, as what you have seen in the previous slide or during the live lectures. We can also push the various register onto the stack and fetch the vector again, right? So this is just an example. You do not need to memorize it. So see in response overhead is there, overhead for responding to each of the interrupt, right? So this is another mechanism for us to quantify the overhead. The final one, if we have external memory with the wait stats, of course, this will take longer. If you have lots of interruption with low priority, and then you have lots of interruption with high priority, so those low priority will be in the wait state, or we can say pending state, right? So we don't want that. And in other words as well, as I mentioned in the live lecture, the ISR code should be kept as short as possible to avoid any unnecessary latency. The following slide here is basically to show you how we can compute the maximum interrupt rate. This is because we can handle so many interrupts per second or even per milliseconds. So how we can compute that is through this formula, right? So Fmax is the maximum interrupt frequency because it's the rate. That's why we express in terms of the frequency. Then we have F-CPU is the CPU clock frequency. Then we have CISR is the number of cycles the interrupt service routine takes to execute. Then the next one is to get the overhead for the number of cycles. How many cycles for the saving state, vectoring, and restoring state. So you can see it's a very straightforward formula to help us to understand the interrupt rate, right? So interrupt rate, the higher it is, it means it is not good, right? Note that the model only applies when there is one interrupt in the system. Another thing to note is when processor, as we know, is responding to interrupts, it is not executing the other code or the other part of the program, right? So that's very important. So how we can calculate the utilization, which is the fraction of the processor's time consumed by the interrupt processing. So this is the formula to calculate it, right? You can see as well, we have to calculate the cycles for the ISR and the overhead. And of course, we have to include the frequency of the CPU and also this as well, the frequency, right? For the utilization. Of course, CPU may look like it's running the code with the CPU clock speed of 1 minus utilization rate times the F-CPU as well, okay? So you have learned about the interruptions with priorities. So now try to have a reflection to think about the interrupts for the program design. How you can think about to use the ISR effectively. So how much work you need to do in ISR. The next one, should the ISR re-enable the interrupts or we can just abandon it? Both comes with pros and cons. So you need to think very carefully in terms of the design. How to communicate between the ISR and other thread. So communication mechanism is very important as well, especially in the data buffering, right? And also remember that we need to ensure the data integrity and if possible as well, to prevent the rest condition. So basically how much work we need to do in the ISR is you need to think about the trade-off, because why we is being termed as trade-off here, because we can't really say anything is perfect. If you want to improve the ISR, you may increase the overhead, but we don't know. So there's a trade-off. You can see faster response of the ISR code will delay the completion of the other code. So it can happen like this as well. in a system with multiple ISRs or a short deadline that comes with the short deadlines that performs the critical work in ISR and buffer partial status results for later processing. So that means that if you had a short deadline, you said you can just perform the critical work at first in the ISR, and then the partial, not the complete result, you can buffer it at later stage.